Very good evening to everyone. You guys have heard of RISC-V, hopefully before this call. And I just want to share a little bit of inspiration that goes behind RISC-V, what has happened a decade back when I started my PhD, right? So obviously you guys are too young to even know RISC-V back then, but it's important to know why RISC-V is a revolution, why it's being treated as the best technology of the decade multiple times, right? And I just want to shed a little bit of insight because RISC-V is obviously very close to me. We started our journey together, and I've been on the RISC-V wagon since its inception. And we now have a company which is commercially supporting RISC-V based solutions, right? So I'm going to spend 15 minutes with you and hopefully inspire you, motivate you to venture into RISC-V, to adopt RISC-V, to contribute to RISC-V more importantly, and to be aware of what RISC-V will be, especially in the coming generations of compute that you see, right? So in the next set of slides, I'm going to introduce what is an ISA, why are they so important in today's world, and more importantly, I'll go on to talk about the different types of ISAs that you would have that people started off with, and what are the contemporary ones that are there, and what are the problems that are faced, right? Both technically and commercially. And then we will see how RISC-V is breaking all those barriers. How RISC-V is this new kid in the block who knows what is right and is doing it right? So what is an ISA? So by the way, feel free, as Vikas said, feel free to stop me at any point. I will be looking at the slide, so don't raise hands, just interrupt me at any point, unmute yourself and go ahead and ask. And the more interactive this is, the good 15 minutes we will have, and then we can probably catch back offline if you have more questions. So what is an ISA? Right. So an ISA is basically a manual consisting of a list of instructions and commands that a software can use to communicate with the underlying hardware. Right. So when you write a program, you only write it using those syntax or those semantics, those keywords that you believe the underlying hardware is going to understand, interpret, and execute. Right. That semantics, that language, that set of instructions is known as an ISA, an instruction set architecture, right? It's like the alphabets of the language or the Hindi language or Chinese one, right? It helps you sentences and it helps you interpret ideas and communicate amongst each other. So to elaborate further, I would like you to take you back almost half a century, take you back to the 60s era. Right? Now, what engineers were doing at that point, right? Programs at that point wrote directly into the machine's unique hardware. Right? So they had one hardware and they wrote software only for that hardware. Right? That was how chips were made. And what is the obvious problem? A program for one hardware did not run on, because it's so specific. There was no notion of instruction sets. You would have just one way of communicating and you would define your entire software based on that. Now, if your company made a new generation of a processor, which is slightly better in frequency, in area, in power, or maybe new features, you dump that software and you start from scratch. Right? Now, looking back, this just looks dumb, right? Why couldn't they think of it? But you would be surprised that this is exactly how a game console, right? Or the C patch they get for some of the game, PCs will not go out of the box, or a PS4 will not go out of the box for Xbox. Each of them needs to be tuned for specific platforms, right? There is no interoperability of these games, right? So don't go judging back your white hair seniors, but this is still evident in our generation as well, right? But hopefully this issue is no longer there. And some of the issues were every time a new hardware was released, software had to start from scratch. Right? Now you had these two teams, but every time you thought of doing a new hardware, you would wait for the entire hardware to get over and then hand over to the software guys. Right? So obviously these were huge cycle times for building anything, and there was no binary compatibility across hardware. build one processor and AMD built a processor and Alpha built a processor. You can't run the same software on all of them. You will have to rewrite your software for each of those platforms, and that's called binary compatibility. Because the output of a G compile output becomes an executable or a binary, right? So there's no binary compatibility across hardware generations. And this obviously made software development an expensive domain, right? Now, this is very shocking in today's world where software is costly, right? So unless it's with an AI, GPT, nothing is expensive software. But back then, software was the most expensive part of building. So someone sat down and said, something has changed, and we tried to problem. This problem was that we need to expose more common functionality. Right? So there are multiple hardwares from multiple vendors, or within the same vendor, there are multiple generations. There's a lot of things, right? There's ALU, which is always there is add common. Why these differently? Can't we all just adopt the same way of, or at least adopt minimal alphabets that are common? Right? So we have to do minimal change. And that's when IBM came up with IBM x86. That was the stepping stone into ISA, right? They did something called an instruction set, and they said to the programmer and the software guys, forget about the existence of hardware, right? Make sure you write your operating system, your kernel, your application, assuming that this is the instruction set given to you, that you can use only these opcodes, only these instructions to build your software. Whenever the hardware comes, it will somehow be able to execute, right? And it told the hardware guys, forget about supporting the software. As long as you support these instructions in hardware the best way you can, software will work, right? And that's when you found separate teams for could start simultaneously. Right? The program enforced was now independent of the underlying hardware. So a software vendor like Microsoft would come and tell IBM that I can port Windows on yours, and the Unix can say I can port it on Alpha, I can port it, and that's a completely different company. It doesn't even need to know what the underlying hardware microarchitectures are. So binary compatibility across generations. Now companies can share ISA, right? I just have to share a PDF between a software guy, and that's enough, right? Both these companies can make money out of the consumers without having to know each other's trade secrets, right? So you don't have one company giving you an entire solution. You can go and aggregate hardware from somewhere, software from somewhere, and so on. So as you see, instruction set is the most crucial aspect between software, right? So everything on top is operating system, virtualization, virtual machines, and blah, 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 all of that happening. And below, you're going to start with processors, SOCs, IO systems, digital design, circuits, transistors, current, blah, blah, MOS, everything like that. Right? In the middle, where the actual transaction happens from one domain to the other, is the instruction set. Right? So it forms the most important part of today's stack. When I say stack, I'm not software or hardware, I'm talking about the entire stack, from transistor to Firefox-based applications or whatever, right? OpenAI, something like that. So what does an ISA include, right? We keep saying instruction. So it talks about multiple things. One is what are data types supported by hardware. Right? For example, does it support integer operations? What is the size of the integer? Is it 32-bit, 64-bit, 16-bit, 8-bit? Does it support floating point? What are the types of registers available? How much memory does it support? What is the RAM size that it has accessible to, right? Then it actually talks about the instructions, right? There's an add instruction, there's a subtract instruction, multiply instruction, and all of that. So all of this together is called an ISA. Now, I'm going to ask you guys a couple of questions, right? Very intuitive words. We're going to answer this question, why ISAs matter, right? So we'll go through a few rhetorical ones. The first one is, why don't we see Intel chips in mobile sets? Right? You've got a Samsung phone, you've got Redmi or Xiaomi or whatever the latest greatest Phantom that is coming out on Amazon, right? Why don't you see i7 or i9 sitting in mobile chips? Any question? Anyone wants to take a jab at it?
So basically, yeah, this is Namrita. Hi, Neil. Can you hear me?
Anyway.
Yeah. Right. Yeah. So basically, mobile chipsets, right? They essentially are low power requirement, right? If you look at all the Intel platforms, they have not been designed for that low power. They did come up with the Atom platform, but there was still that struggle of trying to achieve the lowest power. Uh, uh, which is required, right? That is the one thing. The other thing is you need the ecosystem, right? I mean, just coming out with the platform itself will not help. Like for Windows, you have the entire ecosystem developed for it. Similarly, for any kind of mobile platform, there has to be the support of applications which are available, right? So I think there was a kind of struggle over there as well. They were a little late into the game.
I think, yeah. So if you delve a little more into that argument, right, if you go deep down and actually try to figure out, you'll realize it's actually the instruction set, right? Why am I consuming low power, right? Why can't Intel chips become low power? Why is there adder, multipliers, or their instructions taking? Because they have huge number of instructions which are not relevant for a mobile computer, right? For the things that a mobile processor needs to do, it just needs to have a touch display, or it needs to make calls, or it needs to be able to play some small YouTube videos or play some games and stuff, right? But it needs to remain low power. It needs to still have a good enough frequency. I'm not expecting 3 gigahertz of processor in my pocket, because obviously that's going to burn a hole right through my skin, right? So we don't expect that. But the reason Intel couldn't provide that, as you rightly said, even their attempt through Atom, was because of legacy, right? And that's where ARM was able to take the lead. ARM dominates the entire mobile chipset world, right? Qualcomm, Samsung, everyone. Even Apple, for its iPhones, have variants of ARMs that they started off with later, right? So 99% of the mobile phones and tablets are based on the ARM instruction set. And as you rightly said, a lot of the ecosystem started off using ARM because it was easier, it was better, it was available, and ARM made it so that it's easier to develop applications, it's easier to develop platforms and provide an entire ecosystem to mobile phone developers, right? So no matter how hard Intel tries to enter the market, it's not going to sell because they have the wrong ISA. Right now, I'm just going to take the opposite side and say, why can't ARM partners or people who are licensing ARM cores or building solutions based on ARM, why don't you see ARM servers, right? Your Aadhaar, UPI, all the servers, your bank servers that you see today, none of them are based on ARM processors. Right now, they're making headway since last year, but for a good amount of half a century, you didn't see ARM anywhere close to being a mainframe server. Right? And obviously, your laptops, your desktops, your servers are all AMD based, because there the compute is different. Right? There the requirements are different. There the power is not a restriction, but frequency is, throughput is, performance of benchmarks is. Right? So obviously AMD got something right over there, right? The AMD 64 ISA that both x86 and AMD share is definitely something of value, which ARMs are not able to hit back, right? And suddenly you'll also talk about, IBM still selling mainframes. Now mainframes are like these legacy, decade-old servers that you would see, but you will still see them working. You will still see them that they're present, and it's purely because of legacy, right? It's more than a 50-year-old ISA, but for certain critical reasons, maybe it's a nuclear application, it's a space application, or it's storing some important databases, which you don't want to touch. A lot of things, right? You have to maintain them as is for policy reasons, and the software that was once developed for IBM 360 will no longer work with the new ones, right? And it will require an entire revamp of things. Maybe it's not worth it, right? So ISAs are the most important interface in the computer system. It's where the hardware meets the software, and that's why they matter the most, right? They define the commercial sense. They have defined how people will make money, where you can make money on mobile phones, on servers, on laptops, on desktops, on clouds, right? You can't just pick any processor and put it wherever you want. And that processor has to support an ISA, which will allow it to leverage that particular domain as well, right? So ISAs matter, and you cannot ignore them, right? Large cost to port and view ISA in core of model. Go ahead. Yes, Rahul.
Yeah, so basically, in your last slide, in a way, we can say that based on ISA, like there are three different markets if we consider. So, can there be a single solution which or a set of architect ISA instruction set that can fulfill all the needs, or there can be not like
Yes, and the answer is RISC-V. So
yeah.
that's where we will get to towards the end of my slightly longer than 15-minute talk. RISC-V has the potential to sit in a mobile phone, to sit in a server, to sit in an energy meter, to sit in your smartphone, smart fan, smart bell, anything. Right? It has the
But it is yet to be proved for specifically when we
potential to
see
do it. Now,
for mobile.
it's obviously still
Yeah, correct.
yeah, sorry, there's a lag on my side, so if I'm overlapping with your voice, and I apologize for that. But yes, RISC-V is yet to prove itself in multiple places, but it's made a huge attempt to dominate the embedded world, for example, right? So it's giving ARM the run for the buck, right? So, and it's slowly getting up. So people are starting to realize the monopoly and reasons of why ARM shouldn't be used, and RISC-V has the potential, and RISC-V is evolving drastically. Today, you have people using RISC-V in phones. I mean, trying to build RISC-V for phones, for tablets, for embedded systems, for energy meters, and you have HPC cloud system companies also
That low
placing a
cost
bet
for
on building the
that low
next.
cost for ISA for
Sorry, go ahead.
RISC-V ISA is only because of open source, or like that it is an open source, or is the instruction set also the reason, like the architecture specific difference, like why it stands apart from other?
So we get it. Yeah, I will. Yeah, so we'll just cover it in the next couple of slides. I just have 3 more slides, and I think I should be able to answer all your questions.
Sure.
Right. So I'll just quickly go over this particular slide. It talks about ISAs matter because there's a large cost to changing instruction sets. If you change one instruction, it affects software and hardware. So your entire company goes for a cost. Your entire software vendor, your partners, everyone will have to go to a cost, right? So once you choose an instruction set, do not go around changing, right? And as history has it, it's not often that you come along such instructions or newer instruction sets, right? Only few instruction sets have survived the evolutions of compute over the last 5 to 6 decades, right? It's only x86 and ARM that we heard, but there was Alpha, there was IBM, there was OpenRISC, there was Spark. But, as the world, as you saw it, none of them, not all of them exist today, right? Not all of them have survived the cost of evolution. So you have to be very, very cautious about the instructions that you choose for the domains and everything. So quickly, let's say you're as crazy as me 10 years back, and you said, I want to build a processor. I want to do something of my own. I want to sit down and build, let's say, energy meter. Right? I want to build an energy meter solution. There are 1.8 billion people in India, and every home I want to use an energy meter, so it supports our government and whatnot. Right? It's a small energy meters are small. They're supposed to be low power embedded system. So you say, chalo, theek hai. I'll start with an x86. You open the instruction set, and you see the first alphabetically ordered instruction, AAA, right? It's like a AAA battery. So you'll say ASCII adjust after addition, blah, blah, blah. If you go through that, it's basically a binary coded decimal addition, right? Now, the semantics is actually of no use, but what is of more concern is in today's modern application, including an energy meter or a smart card or something small factor, there is absolutely no use of this instruction, right? There is no way that you can concoct an algorithm which will actually leverage this, right, in today's world, because we no longer do that. But x86 starts with that because of legacy, right? It needs to support all the instructions that it has ever created, and legacy plays against x86 itself. So you dump x86. You say, chalega, theek hai, maybe I should go to ARM. They have more simpler RISC-based instruction sets. Chalo, wo apnata hai. And then you come across this instruction, right? LD, MIA, EQ. It's load multiple and increment address only when the equality bit is set. This instruction writes 7 registers. It forms 6 loads. It also updates the PC. It can cause an ISA change. It's a conditional instruction. Now, just from those 6 bullet points, it doesn't look like a reduced instruction set, right? It's definitely doing more than just accessing registers or operating on registers, right? And if you look at the x86 or the ARM, if you look at the ARM ISA, it has close to 600 plus instructions in the base ISA. And for that one energy meter that you build, you have to implement all of those minimal ones, right? And most importantly, let's say you get through the struggle. Let's say you're a genius and you've implemented a core based on ARM. You can do nothing about it. You can let it rot in your garage, because as soon as you make a product, ARM will come and sue you for licensing, for cost, for revenue, for royalty, and all of that, right? The ISA is not open. You are not allowed to use the ISA. You can refer to it, but you cannot commercialize on top of it, right? Even if you license the ISA from ARM, you cannot modify it. If you find a bug, you're not allowed to disclose it. You are not allowed to talk to someone else who has an ARM license also about what you figured out about ARM, right? So legally, you can't do anything about these instruction sets for your own good, unless you pay millions and millions of dollars to get the highest level access. And still, as you would know, Qualcomm and ARM are still at battle in the courts. It's an interesting read if you're trying to figure out, how the commercials work. Just look at the most recent case between ARM and Qualcomm. Right? It's very interesting. So, considering all the issues that we saw, there were a couple of crazy geniuses at UC Berkeley in 2010, and they said, as a summer project, I'm just gonna get rid of ARM. I'm gonna start building my own ISA. It's a clean slate implementation. I will learn from everything that has happened in the last 5 decades, and I'll come up with a short, crisp instruction set, right? And those are the 4 authors of RISC-V, right? So Andrew Waterman, Jan Lee, Kriste Asanovic, and David Patterson. David Patterson is someone who has won the Turing Award for RISC-V a couple of years back. And from 2010 to almost 2013, 2014, they were then able to release the instruction set that they started off as RISC-V. And that became the first known publication of the first version of the instruction set that was made available to the public. And then the consortium was built around it and so on. Right. So just a quick fact, it's called RISC-V. The V stands for the Roman number 5. So don't call it RISC-V. It's RISC-V, and it's called 5 because there were 4 generations before it that led to a stable ISA, right? So there was RISC-1, RISC-2, RISC-3, RISC-4, and then RISC-V, right? And that's the story behind RISC-V. So as Rahul was saying, right, one of the most important features of RISC-V is that it's open. It's free and it's open. You can do whatever with it. You can add instructions to it. You can subtract instructions from it. You can modify it. You don't even have to ask permission, right? You can do whatever you want. You can add, subtract. That is an amazing business model break from the monopoly of ARM and x86, right? So that gives vendors a good bet to place on something that's new, something that doesn't ask them to invest a lot to start with, right? And not only startups, not only companies, but even academia, right? That's one of the major places where RISC-V has made a huge effect. Now, obviously, there's been a rapid adoption over the last 10 years. I think every Tom, Dick, and Harry, anyone doing any silicon has adopted RISC-V, right? In fact, Intel also joined RISC-V last month. The only person who is not in RISC-V, the consortium, is just one company. And I think you guys know it's ARM, right? So for obvious reasons. So that's what's different about RISC-V. So that was the business aspect as to how it breaks, but it is extremely tiny compared to a contemporary ISA, right? So when Rahul was asking what is the tech behind RISC-V, why is suddenly RISC-V considered? It has only 40 instructions that you need to implement as mandatory. 40, as compared to 600 in ARM and maybe 900 or 1000 in x86 and so on, right? So they've thought it through. They've realized that an instruction set is so crucial that it's going to change for every domain, whether it's AI/ML, it's avionics, it's smart cars, it's smart homes, it's devices, embedded devices, motor controllers. All of them cannot have the same instruction set, But they will have at least these 40 instructions common, and each of those guys can go and build more instructions and connect more instructions together to build more robust, more friendly or domain friendly hardware for that particular application. So it's a clean slate implementation. There's a clear separation between user and privilege specs. And there are no microarchitecture or technology driven mandates. And this is where the game changer is, right? I don't have to RISC-V does not tell you how to implement a 5-stage pipeline or a 3-stage pipeline, or it says that you have to do it exactly this way in hardware. No, it simply says this is an instruction. You can implement it however you want, whether you want to do an addition in one cycle or you want to do it over 32 cycles, do whatever. Software expects you to add 2 plus 2 and give you 4. That's it, right? This allows you to take the instruction set from an embedded processor all the way to a high performance cloud, which has 128 out of order cores and all of that stuff, right? Because the RISC-V does not impose any restrictions on how you design the processor. It only says the processor should be able to interpret these instructions in this format. That's it. And it's extremely modular, as I started off saying. You have the base standard ISA of 40, but there are multiple optional ISAs, right? Multiply, integer, multiply, and division, separate 6 instructions. If you want them, implement. If you don't, ignore them. There's floating point, there's DSP, there's PaxMD, there is supervisor, hypervisor. Everything is optional in this world. It's like building the pizza with only the flavors that you want, right? You want cheese, you want tomatoes, you want olives, whatever you want, you can choose and design a core exactly how you want. RISC-V has all the toppings, and these toppings are constantly being added to, right? People are adding newer stuff, newer instructions for different computes, and they continue to be optional. So if you're a company who is doing these embedded cores, day 1, maybe day 100, you can jump to doing an HPC because everything is on the plate. Obviously, it's stable, additions, and more importantly, it's community driven, right? So they have a very active community, right? Today, we have a compiler, we have an assembler, we have a GDB, an OpenOCD, you've got Ubuntu running on RISC-V, they're doing an embedded version of Ubuntu, Fedora, Debian, OCaml, Python, Linux images, operating systems. There's an effort from doing Android on RISC-V. It's just amazing with the speed with which people have adopted RISC-V to stabilize it, to break away from the monopoly of closed sourced ISAs and to evolve into something that's truly scalable. It's just remarkable, right? So,
question here.
Yes, go ahead.
Yeah, so if we are kind of simplifying the ISA, which means we are kind of pushing the complexity to the software, right? Because there can be different implementations, different companies can do different implementations, and the ecosystem which is going to build around will then have to reinterpret based on what platform I'm using and what is their interpretation of the hardware, right? So, which means the complexity is pushed to the software layer.
In some sense, yes. What you're saying, I understand where you're coming from, and it works in a very. So let me put it this way, right? If I wanted to build a very tiny controller, there is no complexity anywhere. Right? There is no software complexity, there's no hardware complexity. But I want the ability to go from that simple one to a complex one. And RISC-V says, if you feel that my hardware is too simple, go ahead and add your own instructions. Right? If you feel that there is a need to complicate the hardware more, or you need to do a lot more in hardware to keep the software or the compiler simple, you can still do that. You can add instructions. You can reinterpret RISC-V instructions differently in your hardware. You can combine RISC-V instructions to perform just one hardware operation. You can do macro fusion, microcoding, decoding, all of that in hardware. Right? And you can still be RISC-V compatible. So how you draw the line, because the line of complexity, whether it should be hardware leaning or software leaning, is completely on the application, right? And RISC-V allows you to define those on a per application, on a per domain basis. So you have the freedom to do that. You can either build a very strong compiler team and say, okay, I'm going to build the lightweight hardware, but a compiler is. strong and amazing. Come up with, it's going to be processor, which does everything, and the compiler simply just gives one hardware, right? The flexibility to add any amounts of complexity on top of it. So
doesn't that make a
dump of
dependent
all
on
the
the
things that are out there? Sorry,
yes, doesn't that make your entire tool chain of your assembler, compiler, debuggers, everything dependent upon the custom ISA? Like in a way, you are creating a custom, right? You're taking a standard ISA and sort of customizing it, by adding newer functionalities. Now your entire tool chain is kind of specific, isn't it specific to that particular hardware?
so I'm going to ask you this question. If something is custom, unless it is mass adopted, correct? And RISC-V therefore has a community. So it's custom if you and me are the only ones sharing this instruction, right? And then if a million people use it, even though it's just the two of us, it becomes common, right? But if I'm able to get other 20 people adopting it, other 20 processor vendors also adopting this instruction set or contributing to it, and I make it as a standard for this specific domain of compute, it becomes a standard, right? So everything will start as custom on day one, right? But if you prove that you have value, RISC-V will adopt it, right? RISC-V does not want to adopt bad stuff, but it wants to make sure that if they find uses, if they feel that someone wants to contribute and make it a standard, they will enable you, right? So today, if you just look at the screen, right, all these alphabets that you see here on the first column of the table, M, A, F, D, each of them are doing different things, right? The M stands for multiply and divide. A stands for atomic instructions. F stands for single precision floating point instructions. There are 60 instructions in F. There are another 60 instructions in double precision. There are compressed instructions. Then B is for bit manip. J is for just-in-time compile. If you want to do Java-like applications on your hardware, you need instructions in the J. Now, if you isolate each of these instructions, it looks custom, right? Arey, atomics kyun karna hai? I don't have multi-core. Why should I worry about atomics instructions? I don't need vector. I'm happy with 64-bit PaxMD also. So RISC-V says that if you have enough, you can share those ISAs. You need not be the only one in this struggle. If you share them, your solution survives. Someone else's software will survive. Your hardware will survive, and so on. So it is your choice whether you want to keep a secret sauce to yourself and bear the burden of maintaining it and doing everything, or would you like RISC-V to adopt it as a greater standard so that the tool chain, someone is working on the tool chain and everyone adopts it and they start feeling value in what you have contributed, right? So you will have to come to RISC-V with a very open mind and a different business angle. And that's where the fun is, right? So people who are trying to make money using RISC-V have a good challenge and a fun challenge saying, how do I make money by not taking up all the battles on myself, right? And so customization is your secret sauce until you feel that it's too high a burden to maintain it, and you go back and say, okay, maybe I made enough money. I want to reduce my burden. I'll give it to the community because I have an edge, because I was the first one to come up with this custom. Maybe others can slowly creep in and contribute and maybe add value to that. And maybe that's a good business model to start with. So the first few years, yes, you struggle maintaining your own tool.
Got it. Thanks.
Chain so that it becomes a standard. Good. So I'm at the end of my slides and I can take questions if you have any. The last slide is just members. This is just to overwhelm you of the kind of people. This is at least 5 years old, so don't hold me because there are quite a few big names missing. But this is the idea that RISC-V is here to stay. Thank you. The floor is open for any questions, and I'm sorry I've
Neil.
beyond my limited 15
Thank you. So So hi Neil, thank you. So just like for people who want to learn more about RISC-V, what can you suggest, and how do you see RISC-V evolving? I know you are very bullish about it, but yeah, just if you can tell.
Yeah. So I think I had a couple of links here. Yeah. So the last 3 lines, go to the website, and they've made sure that they have plenty of resources for absolute beginners, right? They have Linux Foundation has courses that you can sign up for, which will tell you about RISC-V, teach you about RISC-V. If you go to GitHub RISC-V, you'll see a lot of repositories. You'll see code. You can download the compiler. There are instruction set simulators. You can write a hello world, get started with that. If you are a slightly more mature processor architect or you're an enthusiast, you can join lists.riscvi.org. Now, this is a mailing list which is read-only for the entire world, right? So all the big discussions, all the crazy stuff that people undergo to come up with an instruction set happens here, and it's available for you to read. So if you ever thought, how do people come up with these 60 instruction sets? What's the rationale of defining a floating point add and not a floating point square root? Or why should I include square root in my floating point operations at all? And things like that, right? So the rationale, the discussion, the meeting notes, all of that are captured under different lists at lists.riscvi.org, right? And it's free. It's free for all non-members. I would encourage you to at least join. As an individual, without paying money, you can still be a member of the RISC-V organization. And if you do that, you get access, you can attend calls, meetings on various topics, various new things that are happening in RISC-V. A lot of events that are catered. There are ambassador positions available. There are contributor positions available. I usually, at least for the last 2 years, I've been doing Linux Foundation internships based on RISC-V. This year might be a gap year for me, but I hope to resume them. But if you go to, there's something called Linux Foundation mentorships, right? And every summer and winter, they have these 3-month internships, paid internships, and they will give you a problem statement and they'll assign a mentor to you, and you will be contributing back to RISC-V in different projects. Like someone wants to build hardware, software, they want to build tests, they want to build compilers, they want to do different things over hardware also. Right? So look out for those. Those are really amazing places to work with the community. Right now, just answering the same answer, but from an Indian context. Obviously, in core, I have to promote my company. I can't betray them. But so we do a lot of RISC-V processors, IPs. The journey has started from 2012 at IIT Madras through the Shakti Processor program, which I helped start at IIT. Today at Encore, we build embedded processors. Our current focus is on embedded segment, and we are trying to encroach the market, build innovative solutions. We're truly doing microarchitecture research at Encore. So if you're interested in RISC-V, we have definite openings. Other members in India are CDAC. CDAC is a government spin-off of, they also have their own RISC-V based course. A couple of other companies I would name is Chakra and Mindgrove, who are doing some things in RISC-V. MIPS, for example, has also gotten into RISC-V. So I think if you Google is your best friend, and frankly, I mean, I don't know if you guys are so gung-ho about ChatGPT. I am. So last week, I just asked ChatGPT if it was aware of RISC-V, and it does. It's aware of the entire spec. So maybe that's a good start. That's a new way to start into RISC-V is go ask ChatGPT, take a $20 membership or even the free one and say, can you teach me RISC-V? Can you talk about what are the concepts? Just have a chat. And I think it will teach you enough stuff to get started with.
Thank you, Neil. If anyone else has more questions, please feel free to ask Neil. And Neil, thank you for 15-minute session.
Thank you.
I know you would go longer
Yes.
than 15 minutes. You were very sure about
Yeah,
that.
so this is something I'm passionate about, and no matter how much I try to restrict it, it never goes below 20 or 40 minutes. Yeah.
Does anyone else has more questions to ask?
So Neil,
Yes.
I have one last question to ask.
Yes, go ahead.
Yeah, so for your like in core, whatever the multiple the RISC-V implementations that you guys are creating, like how are you guys solving the verification problem for that?
Amazing. So that's a really good question, because we've got some really a different outlook, right? So I have the liberty to say this because I've made some success recently, but we've been rebels in adopting methodologies. Uh, at Encore, we do not use Verilog to build hardware, right? We use something called Blue Spec system Verilog, which is much higher in abstraction, but it improves your productivity 10x, because in modern world, you're no longer working at the gate level, you're working at a block level, right? So that's on the design side. So we did some more innovative stuff on the verification as well. So for the last couple of years, we've been depending on Python-based verification. So there's this idea of PyUVM, right? UVM is a methodology which is universal verification methodology. It tells you how you should go around verifying. And so far, System Verilog was the the vehicle in which people used to implement test benches, test environments, test cases. But System Verilog is something that's you have to buy $1 million tool to execute System Verilog, right? It's not open, it's not free. The language is free, but there are no open simulators that support System Verilog. So we went to Python. We adopted something called CocoaTV. It's a test bench environment in which you can write test benches, basically control signals and all that in Python itself, right? And it uses a huge abstraction layer of Python all the way to your Verilator simulator and all of that. So using Python as the development environment, we use CocoaTV for test benches. We wrote our own test generators, microarchitectural assembly program test generators, random generators, directed testers. We adopted CocoaTV's cover points in order to define Python-based, coverage, functional coverage. So we've had amazing fun there, and we've made a lot of progress there. We are slowly shifting focus towards new called embedded VM. Right now, this is a new. I wouldn't call it an invention, but it's a new thing that's come from Puneet Goyal, who's been for quite a few years. It's a decade in the making, but it has a solid promise that can beat at least PyUVM or Python verification, or at least by 10x speeds or 3x speeds, right? Because it's multi-threaded, it's multi-core, you can run things in parallel and all of that. Again, this is not what classical do in their life. I mean that if I am placing my embedded VM because it's free, it's open source, and I don't have to pay anyone for it, and I can run millions of threads together if I have the cloud compute for it. So that's what we do about verification. Yeah.
Very nice. Thank you.
Thank you. So Rahul, you have a question?
Yeah, actually, I wanted to ask that the flexibility for, like, suppose 32-bit architecture we are designing. So for that instruction sets, when we compare for RISC-V and compare for suppose x86, so the difference only is about flexibility, or number of instruction sets are fixed in x86. So what is the basic difference which makes RISC-V apart?
So if you look at just the base integer ISA, right? If you take 32 or 64, there are only 40 instructions in RISC-V that you have to implement, and those are minimal ones: add, subtract, shift left, shift right, shift arithmetic left, right, some load, store instructions. Khatam ho gaya, right? 40 instructions. Matlab, second year itself, you could have implemented that. It won't take you more than 4 weeks to write a processor for those 40 instructions. In x86, there is no such thing as modular. There is no definition ki ye kar sakte ho, or you can do something else, or there is this one big mammoth which says this is x86, but there is no part to it. There is no dissection. There is no optional feature. None of that. So you are stuck with the entire thing, of whatever 1,000, 1,500, maybe today it's closer to 1,500 instructions if you compile even the SGX and security extensions, which have been made optional only in the recent years. Right? So that is the biggest thing, right? So legacy, as I said, AAA instruction was something they would have come up in the 60s, 70s, 80s, right? Whenever maybe the 90s when it took off, but there is no relevance of keeping that instruction here today. But if you look at x86, you have to implement it to be ISA compatible. So legacy, I would say, is the summarizing word, which is why x86 is a bad choice.